on a special edition news, the overspreading of bacterial contamination. Bacterial contamination is a major public health concern, which has attracted global attention as it can cause fatal diseases, resulting in an increased death rate of patients and increased medical costs. Lutan will report the latest situation at K San Francisco. Hello, Lutan.
Hi, and I'm at K San Francisco. A lot of patients infected by bacterial contamination were in the worst situation. And now I'm with Namproy, one of patients from this severe impact. Hi, Namproy. How are you?
Not very good.
I hope you get well soon. And now I'm with Dr. Kim Caroline, the correspondent doctor. Hello, Dr. Caroline. How is Namproy's sickness?
Her symptom has been getting worse and seems to be critical.
Sounds terrible.
Yes, bacteria can cause a lot of disease such as diarrhea, food poisoning, typhoid fever. You should beware of bacterial contamination.
Thank you for advice. And now let's go back to the studio.
Thank you, Lutan. And how do we know is there any bacteria contaminated in our daily life? Joining me on the program is an infectious disease correspondent, Sai. Thank you for being here.
Thank you for having me too. As you asked me in the beginning, there are various techniques were used to detect bacteria such as PCR or polymerase chain reaction. This technique should be controlled by high experienced person and it takes a long time. So today, our team are going to suggest two simple ways to detect bacteria. That low cost and rapid bacteria detection. That are gold nanoparticle based and fluorescent based bacteria detection.
In the research, using gold nanoparticle to detect Escherichia coli or E. coli is one of the major foodborne bacteria pathogen. Then they use magnetic nanoparticle and gold nanoparticle with antibody to separate and label E. coli in forming sandwich. They modify the iron oxide nanoparticle with polyethylene for direct immobilization of anti-E. coli antibody. Magnetic nanoparticles were conjugated with monoclonal antibodies and put it in both samples. For separate by magnetic, gold nanoparticles were conjugated with polyclonal antibodies and put it in this sample. For label E. coli, that is from sandwich. This compound will transfer onto a screen-printed carbon electrode that is a chip connected to a potential stage for electrochemical measurements. After that, they have two typical sensorgrams of native gold nanoparticle and native magnetic nanoparticle. Current P of gold nanoparticle is at 0.3 and magnetic nanoparticle is at 0.58. Then they have a DPV sensorgram for the detection of E. coli in different cell contamination, such as 10 power 2, 10 power 4, and 10 power 6 colony forming unit per milliliter. To find the peak current of graph for gold nanoparticle increases with increasing cell contamination. From result, a gold nanoparticle leveraged biosensor has been developed for the sensitive and rapid detection of E. coli. The lower limit of detection is at 10 power 4 CFU per milliliter. Target detection and detection are complete within 40 minutes. Furthermore, sample preparation requires a simple magnet without special equipment. Due to its simplicity and rapid result, this biosensor has been potential of influence used in quickly screening bacterial contamination in food products and water systems.
The next development of gold nanoparticles technique is bacterial detection using antibody-conjugated gold nanoparticles. This research presented a colorimetric method for the detection of Lactobacillus species and Staphylococcus aureus using gold nanoparticles modified with monoclonal anti-gram-positive bacteria. The detection is based on the fact that antibody-conjugated gold nanoparticles can readily identify gram-positive bacteria through antibody antigen recognition, which results in the color change of gold nanoparticles upon aggregation.
The aggregation of conjugated gold nanoparticles leads to the formation of a new absorption band at a longer wavelength. As a result of electric dipole-dipole interactions and coupling between the plasmons of neighboring particles in the form aggregates. The shift of wavelength was attributable to an increase in the local refractive index that was caused by the antibody and resulted from an increase in the local refractive index of the medium that surrounded the gold nanoparticles. The change in color of the antibody-conjugated gold nanoparticles that was stimulated by the presence of lactobacillus could be monitored by UV with spectroscopy, which used for localized surface plasmon resonance analysis, as seen in the figure 1a, and by the naked eye as in figure 1b. It is attributable to the fact that Lactobacillus is more than 5 orders of magnitude larger in size than the conjugated gold nanoparticles, and this TEM image confirmed the increase in shell thickness of nanoparticle after the interaction between the antibody and bacteria. They examined the ability of immobilized monolayer of gold nanoparticles to change in the presence of Lactobacillus species. They found that the absorbance spectrum of the gold nanoparticles exhibit a rate shift in the peak wavelength and a decrease in absorbance at the peak wavelength as a function of the lactobacillus concentration in the sensitivity of 1.4 CFU per milliliter and a detection limit of 105 CFU per milliliter in pure culture of lactobacillus species. The same methodology was used to detect Staphylococcus aureus. The plot of the change in absorbance as a function of the Staphylococcus aureus concentration indicated that the detection limit was 120 CFU per milliliter. To verify the reliability of the immunosensor, they identified gram-positive bacteria in samples of sugarcane using their development method and conventional counting methods. The amount of bacteria agreed closely with the values that were obtained by traditional microbiological colony quantification.
As you know, that bacterial detection takes a long time and complicated techniques. Let's think how good it would be if you just dip this paper into the water. Then you get the result in 5 minutes. If you want to know, let's see together.
To create the colorimetric response need for visual detection of bacteria, a sensor is adapted by using beta-galactosidase and nanoparticles. That cationic nanoparticles were electrostatically bound to anionic beta-galactosidase, causing competitive inhibition of enzyme when incubated with colorimetric substrate or chlorophenol red beta-D galactopyranocyte. The color of sensor remains pale yellow, but when negatively charged bacteria are present, a competitive equilibrium is formed between the bacteria and the enzyme for the nanoparticles that restore enzymatic activity to beta-galactosidase, which then creates the colorimetric substrate to produce a deep purple color. Before printing, the enzymes with nanoparticles and CPRG were filtered through polypropylene membrane. Then the enzymes and CPRG were silenced into black and yellow ink respectively. After printing onto paper test strip, Immerse the paper into analyzed solution for 30 seconds and remove for drying. After 5 minutes, the strips were evaluated in two cases. If it shows yellow color, that means uncontaminated bacteria. But if it shows purple color, that means contaminated bacteria.
ตื่นค่ะ ตื่นค่ะ
The research used the changing of fluorescent spectra in order to indicate the appearance of bacteria. Azo reductase was extracted from Clostridium perfringens cell. It used to reduce its azo bridge in the probe to be monomer and with ammonium salt, which exhibits fluorescent indicative of densyl monomer. From the report, they used the advantage of azo reductase activity of bacteria and the previous myo-inositol fluorescent probe, which has reduction of azo group in the static range. They combine this approach to design probe 4 as a cyclohexane base, which uses this azo group as a bioreductive trigger for a conformational ring flip. The synthesis of probe 4 and its monomer used the reaction of diazobicyclooc and densyl chloride. After that, they synthesized the dimer 7 from hydrogenation of probe 4. After use, azo reductase react with 7. It generated with ammonium salt. It will undergo a ring flip to be more stable. They proved the bacterial detection ability of probe 4 by fluorescent spectra observation. As you see in the picture, the blue line is the dimer type emission. After monitoring 12 hours, it shows the appearance of a monomer band or red line at the different wavelengths. So it implies the changing of dimer to be monomer fluorescent. The change in fluorescence spectra of probe 4 is consistent with reduction of azo bit trigger to give the monomer fluorescent probe 7 in its ring flip conformation. This probe didn't require much technical experience and a lot of device. Therefore, it is a simple way to detect bacteria.
The research was using fluorescent quenching to indicate bacteria. They used Escherichia coli or E. coli and Staphylococcus aureus or S. aureus to observe different patterns of gram-negative and gram-positive bacteria respectively. The chemical substance that they used was FPVP. FPVP was synthesized by CCDP IR825, boron dipyromethane or BODIPY, conjugated with polyvinyl pyrrolidone or PVP, using quaternization reaction. The structure of FPVP. The interaction between FPVP with bacteria was expected to fluorescent quenching. The fluorescent property was observed by L550B luminescent spectrometer and LSM510 confocal laser scanning microscope. And how does it work? From the research, they show that they can detect in liquid and solid phase. I will tell you about liquid phase first. They added FPVP solution into bacterial solution, incubated for 1 hour, centrifuge it and wash it by PBS to remove unreacted FPVP. For results, S. aureus show lesser quenching effect than E. coli because negative charge of S. aureus is located in the long chain of teichoic acid that reflecting the dominance of hydrophobic interactions. They use SEM to prove the presence of bacteria. For the solid phase detection, they use PP film coated with FPVP. It emits green fluorescence under a laser scanning microscope. They put PP film in bacterial solution, incubated it for 1 hour, and washed it by PBS. The color chain of PP film indicating the presence of bacteria. FAPVP was used to observe the interaction bacterial cell with coated PP film. Finally, the bacteria were killed by heat. Using NIR irradiation, the efficiency is almost 100%. This is the image of bacteria by SEM after use NIR irradiation for 5 minutes.
From the research, they designed a QMNP fluorescent polymer system
For detection and identification of bacteria, 3-QMNP fluorescent polymer constructs are combined to differentiate bacteria cells according to the characteristic response pattern. To avoid the interference of QMNP fluorescent polymer construct in the measurement system, the construct can be separated quickly by a magnet.
For process of this work, first they prepare this egg type of bacteria. Then synthesis of fluorescent polymer. A polymer functionalized with side chains carboxylic acid group was synthesized using a method reported with modification. Next step, preparation of functionalized magnetic nanoparticles. For next step is QMNP fluorescence polymer construct. PFBT was placed in the centrifuge tube and the intentional fluorescent intensity was recorded. Then the QMNP fluorescent polymer complex was removed using magnetic separation and the fluorescent intensity of supernatant was measured again. The last step is linear discriminant analysis of bacteria identification. A bacteria solution was added into each tube and incubant. Then the QMNP was removed using magnetic separation. One of the techniques that used in this method is chemical nodes. Chemical nodes need to be trained with qualified biological samples so as to build a database of reference. Then the sensor system can recognize new samples by comparing the database. For chemical node of bacteria identification, addition of bacteria sample results in a variety of fluorescent response due to which the PFBT was derived in the solution from the competitive binding ability of different bacteria cells. For each bacteria sample, we measure its response chain against the 3-QMNP polymer. The fluorescent response matrix was analyzed by LDA. Their approach has been used to measure bacteria within 20 minutes. Combined with UV vis measurement, the method can be successfully performed to identify and detect 8 different bacteria with high accuracy. The results certainly demonstrate that their chemical nodes hold a significant promise of identification and detection of bacteria.
If I know there are bacteria detection by gonadotrophic and fluorescent that are low cost, simple and rapid, I would not be like this. But for preventing bacteria, we want high sensitivity detection that can detect bacteria out of small amount and can analyze specific bacteria in order to destroy it in time.